In this example, we want to find the directional derivative of the function fxy that is equal to x cube y square at the point -1 and 2, that's my x0, y0, in direction of the vector a, 4i minus 3j. I'm not given the unit vector. So what I need here to apply my result formula 5, I need the partial derivative of the function respect to x, respect to y at the point -1, 2. I need the unit vector. So I go step by step. First I find the partial derivatives. I find my fxy, fx of x or y, the partial with respect to x-axis. My y is constant. I get a 3x square y square. Then I find my derivative with respect to y, that's partial y. Again, my x is constant. I get here 2x cube y. I want to find the values at the point -1 and 2. F of x at the point x equal to -1, y is equal to 2. I get here 3 minus 1 square into 2 square. The -1 square is equal to 1 and 2 square is 4. 4 into 3 is 12. So if and then I find f of y at the point -1 and 2, again here 3 minus 1 to the power 3 and y is 2. So that gives me -6. Now I got here. Now I want to find the unit vector. I given a vector here. I have given the vector u, a. Vector a is equal to 4i minus 3j. To find the unit vector, I need to apply u is equal to a over magnitude of a. And to find magnitude of a, I just take here my magnitude of a is equal to root of 4 square is 16 plus 3 square is 9. 3 is 9. It here 25 minus 3 is 5. What's my u? My u is equal to a over magnitude of a. So that's equal to 4 over 5i minus 3 over 5j. So I have the values for the partial derivatives and also that one. Now I apply my formula. My formula is the directional derivative of the function at the point -1, 2 along the vector u, unit vector u is equal to f of x at the point -1 and 2 u1 and plus here my u1 I have already calculated, so I can put the value of u1 also, and I can simply write that this is equal to 4 by 5. Here is my u1, that is here 4 over 5. 4 over 5 my plus I'm having here the derivative of the function f of y at the point 1, 2, and here minus 3 over 5. This is my u2. So I substitute the value of the partial derivative. That's equal to 12 into 4 over 5. Then plus here -6 into -3 over 5. Simplify this one. I get here this equal to 48 over 5 plus 18 over 5, and that give me here 64 over 5. That's my directional derivative of the function -1, -2 in direction of vector a, that's 4i minus 3j. I take another example and we want to find the directional derivative of the function x cube sine 2y. We have trigonometric function at the point 1 pi by 2, and here we having in the direction of the vector a, that's equal to 3i minus 4j. So again we need the partial derivatives and we need the unit vector. So to get the, we have the formula here. We want to find the directional derivative of the function fxy in general formula. This here is f of x, xy u1 plus f of y xy u2. So I want to find at the point p1, so we can write here directional derivative of the function at the point 1 pi by 2, x equal to 1, y is pi by 2, f of x 1 pi by 2 u1 plus f of y 1 pi by 2 u2. So I find the derivative of the function at the point, partial derivative of the function at point 1 pi by 2, and find the unit vector and substitute in this this equation, and we get the result. Now here is my f of x, xy, y is constant, is equal to 3x square sine 2y. I find here f of y, xy, that give me 2x cube cosine 2y. Derivative of sine 2y is equal to cosine 2y, and derivative of 2y is equal to, so get a 2 cosine 2y. Now we find the value of this one, f of x at the point 1 pi by 2. So I get here 3 into 1 sine pi. Sine pi is 0, so we get here this equal to 0. Now we are having the other one, that is f of y 1, and here y is pi by 2. So get here 2 into 1 into here cosine pi by 2 is cosine pi. Cosine pi is equal to minus 1. So we get here 2 into 1 minus 1 is equal to minus 2. Now I have to find this my result 1. We are having here the value of the partial derivative at the point 1 pi by 2. Now I have here vector A. Vector A is 3i minus 4j. So magnitude of vector A is equal to 9 plus 16 under the root is equal to 25 under the root is equal to 5. So my unit vector is A divided by magnitude of A is 3 by 5. And we having here I minus 4 by 5. We have here j. So now I substitute the values in the directional derivative of the function at the point 1 pi by 2. So we having here this is equal to 0 into 3 by 5 when the derivative of the function with respect to x is equal to 0. And now we go to the next one. Then the derivative plus derivative of the function with respect to y, that is minus 2, and u2 is minus 4 by 5. We simplify this one, we're getting this equal to 0 plus 8 by 5. So we are having here the partial derivative, the derivative, directional derivative of the function. The point 1, 2 in direction of vector u is 8 over 5. I'm going to use this equation that we are having here, equation 5. We have a directional derivative of the function fxy in direction of u, that was f of x y, f of x xy u1 plus derivative with respect to y u2. I use this one, we can rewrite this one as a dot product. When we write this one as a dot product, we can have here the derivatives. We take separately of x xy I plus f of y xy j dot u1 I plus u2 j. So it's a combination of the two vectors. One vector is the containing the partial derivative, other vector is the unit vector. The vector which is containing partial derivative, we denote this by a name of a gradient. We write as gradient of f or del f. We can write in both way we like. So we say the definition of the gradient will be, let fxy be a function of two variables. The gradient of the function xy is a vector value function, that is the gradient of f is equal to fxy I plus fy xyj. So that we get the operator. We say this is the differential operator. As we having this d by dx, this is a differential operator. Then we have partial by partial x is partial derivatives, they are differential operators. And also here we have the gradient. The gradient is the operator partial by partial x I and plus partial by partial y j. So here you can see when we are defining here this only derivative with respect to x, then here is a partial derivative. When x is changing, no other variable is changing. Y is changing, no other variable is changing. Here we are having the function of two variables, and we have this gradient or del. This is our definition of that one. The operator, differential operator is partial x by partial I, partial y, partial j. In the 3 dimension, then this gradient we will define del as partial x by partial I plus partial y by partial y plus j into j, partial pi partial z. Okay, so this will be in 3 dimension. If we are having here, I take as a note, we have the function fxyz, a 3-dimensional function. This is a 3-dimensional function, and we want to find 3 variable. Find the gradient. The gradient of the function, we can define the fxyz is, we can just have here the gradient of the function. We can write as I told you, we write here gradient as grd as a gradient, grad, gradient of the function, or we write this one as the del of gf, or we can write here this is equal to partial f by partial xi plus partial f by partial yj plus partial f by partial zk, and this is a vector value function. For this vector value function of a scalar function, fxy, z or fxy is scalar function. We take the derivative the gradient of that one, that become a vectorial function. It's having a lot of application in physics, in engineering, in different fields. The gradient is having a lot of application because this give me the variation. For example, we have 3 dimensions, give me the variation in x, y, z, and 3 directions simultaneously. Not we are going to fix one, we are taking one other as a constant, no. So it's having a lot of application. We are going to see the formula, the change in formula in the this directional derivative. So here is, we take as a note, this is also a note. So we are having as a second definition of this gradient, this function, this directional derivative of the function. This was here f of x, xy, u1 plus f of y, xy, u2. So as I mentioned above, we can write this one as a function 2 variables. We can have here f of x, xy, I plus f of y, xy, j, and dot product. We have u1i plus u2j. So I can write this is my gradient. I say is a gradient of f, then dot here unit vector u. So my definition for the directional derivative of the function xy, it can be at any point. So is equal to gradient of f dot unit vector, this is dot product, this is the application of the dot product also, into u. Here we can have this, say this is my node 2, this is my node 1. I take here node 3, and now I am having here the function of variable, 3 variables. We have the function f, x, y, z, and the directional derivative. The directional derivative of this function, derivative of function f in direction of unit vector u. So node 3, we are having given a function of 3 variable. Function is function x, y, z. We want to find the directional derivative of this function in direction of the unit vector u. So I can write here the d of directional derivative of the function x depending upon x, y, z in direction of vector u. You can define this one as gradient of f, where f is a function of x, y, and z, and into unit vector u. I explained you with the help of the example that how we apply this gradient formula or to find the gradient of the scalar value function at a certain point. The example is that find the gradient of the function. We have 3 variables x, y, and z. Y z cube minus 2x squared at the point P, there is 2 minus 3 and 1. So we have the formula for the gradient. Gradient of the function is defined is equal to the function f of x, I plus f of y, j plus f of z, k. So we find the partial derivative, then we take at a point. So the gradient of the function at any point x, y, and z, we take the derivative with respect to x. First one is y, z cube, they are constant, only x is changing. So get minus 4 xi. Then with respect to y, so we have plus z cube j, and with respect to z, we are having here plus 3y z square k. So as I told you when I was discussing the partial derivatives, I told you it's very important and we have a lot of applications. You see every time we are using this partial derivative concept. So again, I will recommend strongly that you do a lot of problems regarding the partial derivative so that you master this one and the things become easier for you.